we're going to talk about risk analysis in this segment. I'm going to get my screen up here that we're going to share, PowerPoint presentation, and we're going to get going. There's a lot to cover in this section. Okay, risk analysis. This is kind of the second step of the analysis, the third step overall. For those hazards and risks that have been identified, which we did in the previous step, an understanding of the potential risk levels they present is determined during the risk analysis phase. Risk analysis includes the estimation of risk, which takes the causes and sources of risk into consideration, as well as the severity and likelihood of consequences. Analysis methods can be qualitative, semi-quantitative, or quantitative in nature. Qualitative methods use words such as high, medium, and low. Semi-quantitative methods describe risk using numerical rating scales, but are not typically based on statistical data. Quantitative methods are less common in that they derive rating from statistical data, which is not commonly available in general industry and won't be used in this course. However, risk levels using any of these methods are still estimates at best. So when we take something like a risk matrix and we say it's low or something like that, and then we give it a number, we're kind of making that a qualitative into a quantitative. So that's what a semi-quantitative method is. Risk analysis follows this section of sequence of action. Determine the effectiveness and reliability of controls, analyze nature and magnitude of consequences, analyze likelihood, and measure risk. And we'll go into each one of these in a little more detail. Determine the effectiveness and reliability of controls. Risk level depends on the effectiveness and reliability of existing controls, if they're already in place. If some are already in place, at least. Questions to ask are, do the controls reduce and maintain risk levels to an acceptable level? Are the controls acting as intended? Do they do what they're supposed to be doing? Can the effectiveness of controls be tested and demonstrated? Is it possible for controls to be intentionally disabled, defeated, bypassed, or minimized? If so, how easy is it to detect this? As you know, as a rule, engineering controls are more difficult to be bypassed or minimized, whereas somebody has to take off a guard, they usually have to have some tools or maybe some specialized tools. But administrative controls are pretty easy to bypass. I've heard of people saying, supervisors saying, here, sign this paper saying that you've been trained in something, and I'll give you your paycheck. And that, if you ever find that happen, you got to stop it, because that's not the right way to do it. Are there escalating factors that can reduce the effectiveness or reliability of controls? Do the controls work in concert or separately? Are they dependent on or independent of one another? Analyze the nature and magnitude of consequences. The types of consequences an event can have and their potential severity are determined. An event may have more than one consequence. This analysis should consider existing controls with all relevant contributory factors that have an effect on the consequences, how consequences impact the organization's objectives. In other words, how this event as a consequence, and what that could be, is it really detrimental to the organization's objective? Is it just marginally detrimental? Analyze the nature, magnitude of consequence continued, immediate impacts and acute consequences, long-term impacts and chronic consequences. We all know what the difference between acute and chronic is. Secondary consequences or cascading effect on other stakeholders of the system. Secondary consequences would mean a consequence in addition to the primary consequence, or a cascading effect, meaning A causes B, causes C, causes D, which could happen. And other stakeholders of systems. Stakeholders, as we know, is a general term that means basically anybody that could be affected by what we're doing here or by the system that we're talking about. Analyze likelihood. Likelihood of occurrence can be determined by three common methods: historical data review, predictive analysis, or expert opinion. A review of historical data of incidents or exposures is performed to extrapolate a probability of occurrences based on past experience. This requires a sufficient number of past experiences to project the future likelihood. Well, again, historical data review, one of the most common places that we as safety professionals go is OSHA logs and workers' comp claims. When adequate historical data are not available, forecasts of future likelihood can be developed using predictive analysis. Methods such as fault tree analysis and event tree analysis of the system or activity and its failure modes can be used. We'll talk about failure modes later on. Data such as operational experience, industry experience, or published data are used to estimate the likelihood of an event. The possibility of various failures of different parts or components arising from the same cause should be considered also. Operational experience, in other words, what the people in your plant or your company have, what kind of experience they have, not just the managers and supervisors, but talked about the people that run the machines, people on the floor. Industry experience, industry organizations are great. You can find out maybe you've never had experience with this particular operation, but somebody else might have. And generally speaking, as we know, safety professionals are pretty open to sharing with each other. They really have want the safety of their people is their main goal. It doesn't matter if it's with your company or somebody else's company. Likelihood analysis can also involve experts in the development of likelihood estimates. Typically, an informed or more formal process involving internal or external experts is employed. One of the ways you can do this is an outside consultant. At OK Foods, when we did our process hazard analysis, we had an outside consultant. He had been to a lot of different companies that used anhydrous ammonia or other highly hazardous chemicals. So he had a lot more to bring in on the likelihood of an event happening, because he had a lot more total experience than anybody that we had. Measure risk. Again, risk is measured and expressed qualitatively, semi-quantitatively, or quantitatively. Qualitative methods, again, use words such as high, medium, low. Semi-quantitative methods describe risk using numerical rating scales, but are not typically based on statistical data. Now, that's when we say this is, the severity is medium, and the likelihood's medium, the consequences are medium, and we come up with a number. That's semi-quantitative. Again, strictly quantitative methods are derived from statistical data, so they're not really available most of the time. So, and also quantitative and semi-quantitative measures can only be used to compare risks with other risks measured in the same way. So what they're saying here, if you're not using the exact same risk matrix, and we're going to use the 5x5 in this class, then you can't compare it to a risk measured by a different matrix. How do you compare a 7 to a B anyhow, right? Assess severity of consequences. Review available information, experience, historical data, expert opinions, and best practices should be considered. Also consider frequency and severity of incidents, property, equipment, or asset value at risk. In other words, what's the asset value? Is this piece of equipment hugely important to the company, an expensive piece of equipment, or is it just a relatively minor one? Degree of business interruption. Well, if this fails, will it put us down for 5 minutes or 5 days? Environmental damage. If this gets out, what's it going to do to the environment? Not just on our property, but off our property, and will the public be affected? Determine occurrence probability. Likelihood is the chance of something happening, and is sometimes referred to as probability. Probability is defined as an estimate of the likelihood of an incident or exposure occurring that could result in harm or damage. Consider frequency of task or event, the duration of it, how long does it go on, the population exposed. Let's say population here, not just population outside of your facility, but your employees too. Safety, health, and environmental exposures. Well, that covers a lot, doesn't it? Dose and exposure assessment. How big is the dose? What kind of exposure is there? Define initial risk by using the risk matrix established as part of the risk criteria. Remember when we started the operation here, we determined what risk matrix we're going to use. By applying the combined severity level and a current probability level, a risk score is determined that provides a visual representation of where risks are ranked to help decision makers manage risks. So in other words, that risk score you come out with after you do the risk matrix is just one that you compare with another one that's done on the same risk matrix to kind of put things in proper perspective and line and determine which risks need your attention first. Select and implement risk reduction methods. Select control measures from the hierarchy of controls. And you should all be familiar with the hierarchy of controls. Assess residual risk. Following the addition of any controls, a second risk analysis is performed to determine residual risk levels. Residual risk is defined as a risk remaining after risk reduction measures have been taken. There are many hazard and risk analysis methods. The simplest ones that provide the necessary information should be used. Assessing risk presented by identified hazards is key to risk management. It provides risk-based information so decision makers so that the most appropriate risk levels can be selected to achieve an acceptable risk level. Risks are derived from exposure to hazards. Risk is measured by the likelihood of the exposure or event occurring and the severity of consequences if it does, likelihood and severity. For a hazard to present a risk, there needs to be an exposure to people, property, environment, or other valued assets. So in other words, to be a risk, there has to be some exposure of a hazard to people, property, maybe, or the environment. It could be anything, but some kind of basically damage to somebody or something. All right, hazard and risk analysis steps. A hazard and risk analysis should be conducted in a systematic manner using the following steps. Develop a plan. Define the scope, purpose, personnel, resources, budget, timeline, and other elements needed for the effort. The method for analyzing hazards and risks should be determined. Define responsibilities. The roles, responsibilities, and line of communication within the organization should be defined. Analyze hazards, exposures, and potential failure modes. There's that failure modes again. Be sure to include potential failures that could lead to the exposure. How and why hazard exposure and or failures might occur. The conditions and causal factors that can lead to exposure or failure modes. The frequency and duration of the task, event, or condition that could lead to exposure, and the affected parties, property or assets exposed to the hazard or potential failures. There we go again, frequency and duration, and then what's affected by it. Analyzing existing controls. Using the hierarchy of controls, the efficacy of existing controls for the identified hazard are analyzed to determine levels of effectiveness and reliability. Part of the analysis should include the ability to defeat or minimize existing controls and the ease of doing so. Again, a control that can be easily defeated isn't probably going to work very well. Analyze severity of consequences. Credible scenarios and consequences associated with hazard exposure or failure mode are identified and listed. Those consequences that present the greatest credible severity are the first selected for analysis. At this point, the hazard analysis has been completed. The following steps constitute a risk analysis. Analyze and estimate likelihood. The likelihood of the occurrence of an estimated hazard exposure and or failure is analyzed and estimated. This requires a review of available information, input from knowledgeable stakeholders and experts, and statistical data if it's available. Note, likelihood is a general term that can be expressed as a frequency or probability of the future occurrence of the consequence scenario. Frequency is based on a rate measure and requires a denominator, such as time, number of tasks or products produced, or other measure during the life of the system, process, or product. Now, frequency means a rate, means a denominator, such as like miles per hour or units per day. That's your denominator, the hour of the day. Probability is an expression of the chance or odds of something happening, and it's usually a pure number, such as 1 in 100, which is the same as 1%, or 0.01. All three of those things be the same thing. Estimate risk level. Once severity and likelihood risk levels are estimated, they are combined according to the selected risk scoring formula to derive a risk score level. Hazard and risk analysis are often performed at the task and job level. Some analyses are the result of a larger, more comprehensive risk assessment effort covering a process or an operation. Tools used to analyze risk. There are many tools used in analyzing hazards and risk in a risk management system. Preliminary hazard analysis, PHA. Don't confuse this with a process hazard analysis, which is also called a PHA, which is required under process safety management, and we already talked about that in previous modules. But this is initial systematic analysis of a system design, facility, or process used to identify hazards and control measures. What if analysis? This is a team-based brainstorming process used to identify and analyze hazards of the system or process. In other words, you say, what if? What if this happened? What if this happened? And you kind of come up with the most possible things you can come up with, whether they be big or small. But failure mode and effects analysis. This is a detailed qualitative or semi-quantitative method used to identify and analyze ways in which system components can fail and the resulting effect of the system. We're going to go into depth about this in a little bit. Layers of protection analysis. This is a barrier analysis used to study existing or proposed barriers for a hazardous scenario or situation. Bow tie analysis. This provides a big picture view of a hazard scenario and its relationship between hazards and causes. And a striped bow tie risk analysis, similar to a bow tie analysis, but designed to provide more detailed risk-based information. This is analysis that comes out from both ends, and they kind of meet in the middle. It looks like a bow tie. I've never seen it used, but it's out there. What if checklist? This is frequently used during a process hazard analysis under process safety management. We went into a little bit of detail on that. We'll talk about it just briefly again. What if checklist? Okay, this is a method that was illustrated in the PHA portion of the process safety management. It uses 9 columns, and a sample is shown here. Now, this is the what if checklist kind of thing. What if? The questions is the what if. And they almost always start with what if. There's your first clue. What if the safety relief valve fails to lift at the set pressure? Safety relief valve is a valve that's on a pressure vessel. And if the pressure vessel's MAWP, or maximum allowable working pressure, is, say, 300 PSI, then your safety relief valve should go off at 300 PSI. Scenario then is an overpressure condition exists, causing a leak or a rupture and an NH3 release. NH3 is anhydrous ammonia. Anhydrous just means without water, so that means more like pure ammonia. Consequences: employee injury or fatality, community evacuation, environmental contamination, plant evacuation. Remember, the scenarios here: an overpressure caused a leak or a rupture. A leak of a tank probably wouldn't be too bad, but a rupture would really be bad. Now, what are the controls? 5-year change out of SRVs, preventive maintenance program. At OK Foods, we had a change out, a 5-year plan to change out every safety relief valve in the whole company was changed, put a brand new one in. Everybody just changed with one another every 5 years. And to make sure that this was the right thing to do, we took some valves, like I think a half a dozen or so out of plant 2, that had been in place and in use for 5 years, sent them out to be tested, and every one of them passed. In other words, every one of them failed at the pressure they were supposed to fail at. They were released, I should say, at the pressure they were supposed to release at. So that kind of confirmed that our 5-year change out of SRVs was the right thing to do. And then we had a preventive maintenance program, which helped overall. So anyhow, the consequences was considered 4, potential for single life-threatening injury, which was pretty high, but the frequency was a 1. So it came up with a C, which is action may or may not be needed. And so we didn't have to take any action on this particular item. But that's a what if checklist there. The question is the what if. In other words, the question is the what if part of it, the description of the failure that could occur. The scenario is what would happen if the failure occurred, and then the potential consequences of such a failure are given. The control in place is a program to replace all SRVs every 5 years and an ongoing preventive maintenance program. The team then refers to the IIAR risk matrix and has determined that the consequences are pretty severe, but the frequency is low, so nothing had to be done, and there are no recommendations. Even though it's considered part of risk analysis, evaluation was also accomplished by going through the risk matrix. Now, failure mode and effect analysis, FMEA. We're going to talk about this in a little detail. Another method of risk analysis is the failure mode and effect analysis, which is a more detailed method to identify and analyze the ways in which system components can fail and the resulting effects to the system. In it, the system is broken down into individual components or modes, which are then systematically analyzed for the different ways it can potentially fail and the effects of each failure in the system. The steps are establish context, purpose, and scope. Notice a pattern here. The systems to be analyzed, time frame, what limitations there are, resources, and definitions to be used. In this example, severity will be multiplied by likelihood, and this product divided by the prevention effectiveness to get to the risk priority number. We'll go over the prevention effectiveness in a little bit. Select a team, an experienced facilitator, and a qualified cross-functional team from safety, engineering, production, quality assurance, human resources, operators, outside experts or consultants, and others as appropriate are selected. Cross-functional team, that's a good idea to have people from all over, because you've got to have somebody from safety, you've got to have somebody from operations in there, and if you have somebody from engineering, that will probably help too. Gather data on the systems, operations, procedures, diagrams, loss history, and other available information. Include any previously performed hazard analyses. So if you have them before, include them too. Identify process functions. The primary functions or process steps are identified for analysis. Each of those functions or steps. Each is entered into the first column of the spreadsheet. Identify failure modes for each function. There may be multiple failure modes for a function. Those are listed in the second column. What's a failure mode? That's just whatever could fail. It's pretty simple. Just just a fancy term for the what failed. So identify effects for each potential failure mode and put them in column 3. This step is critical and must be studied carefully by the team. In other words, if something failed, what can happen? Determine the severity for each effect. And here's an example of severity on a 5x5 matrix. Insignificant, negligible, marginal, critical, and catastrophic. And they're 1, 2, 3, 4, 5. Identify potential failure causes, entering column 5. This requires a close review of past experiences and previous loss analyses, observations, and experiences. Determine likelihood for each cause and record in column 6. This is again 5x5 matrix. There's your likelihood: unlikely, seldom, occasional, likely, or frequent. Identify existing controls, if any, and put them in column 7. Determine preventive effectiveness. Using the hierarchy of controls, the team evaluates the effectiveness and reliability of existing control measures, okay, which you have just identified here. Assign a prevention effectiveness rating and enter in column 8. Now you can see that this list is going to kind of go down the hierarchy of controls. It's going to give you a preventive effectiveness of 5 if you avoid it or eliminate it. Obviously, if you avoid or eliminate the whole thing, there's not a risk, is there? Substitute or multiple engineering controls. In other words, you substitute something else or multiple engineering controls. I don't know what, they're kind of fuzzying things up a little bit, and I don't particularly care for it, but this is what they had. Single engineering control, and in my mind, a single engineering control that's effective is just as good as multiple engineering controls. Warning or administrative control. Again, some people want to put warning as between administrative and engineering controls, which I disagree with, because warning is an administrative control. And then PPE or none. And those, if you get that a 1, that's just basically they're saying there's nothing there. So they're giving PPE the same as none, which I get that. Combine severity and likelihood ratings. Multiply the severity from column 4 by the likelihood from column 6 to provide a risk rating, which is entered in column 9 and again in column 14. And calculate initial risk. But the reason why we're putting it in 9 and 14 is that's the initial one, and we're gonna use it right now, and then we threw it in the column 14 because we're going to use it in a couple steps later. Calculate initial risk. Divide the number in the column by the prevention effectiveness from column 8 to get the initial risk priority number, RPN, risk priority number, presented in column 10. Okay. Yeah. Okay. Okay, I'm column 9. I didn't put column 9 there. Divide the number in column 9 by prevention effectiveness in column 8 to get the initial risk number, which is entered in column 10. This is what the worksheet looks like after this step. So we have, and this is the lashing ship containers now. And the process, column 1, is handling a lashing rod overhead. The potential failure mode is fall from elevation. Potential effective failure is death. So it must be pretty high fall, doesn't say it. So that severity is pretty heavy, right? I got my glass on C's number. Is 5. Severity is 5. Potential cause of failure, unsafe practices. And the likelihood is a 3. And the current controls are none, which is kind of amazing that they're doing this with no controls whatsoever. So the preventive effectiveness is a 1 because no controls or PPE, that's a 1. So S times L is 5 times 3, which is 15. Now you take the S times L and divide it by the PE, and that's why you get the RPN. That sounds like high school algebra, doesn't it? And so you get 15. Well, 15 is pretty high, isn't it? And I would say so too. Somebody's up on top of something with no controls whatsoever. I'd say it'd be pretty hazardous. So they're looking at this and say, man, this is hazardous. We got to do something about it. Now, additional controls. For initial risk priority levels that are considered above the acceptable risk level, additional risk reduction controls are selected using the hierarchy of controls. Enter such controls in column 11. For each control, identify the responsible party and target date for implementation and record in column 12. This is a good idea. When you decide to do something, you got to have somebody that's responsible party. So for each control, you're going to say, okay, this guy's going to do it, this group's going to do it, and this is going to be done by this date. If you don't do that, you know what? There's a good chance it's going to get done. Verify actions taken. Following implementation of added controls, a review is performed to verify that the controls are effective and no additional or unintended consequences are created. Enter in column 13. Reassess preventive effectiveness of the additional controls and record in column 15. Calculate the revised risk priority number by dividing the number in column 14 by the number in column 15, or write down this number in column 16. This is the revised risk priority number. The rest of the worksheet after adding the additional controls is this. In other words, this whole thing is called with additional controls. So the needed actions were railing, SOPs, PPE. Responsible party and the due date was just management. I picked the due date. The actions taken, they install a railing, adopt the SOPs and PPE. That's actions pretty generic there, but that's to give you an idea. Again, number 14 was very likely, it was a 15, if you remember, and the PE, the preventive effect, was a 1 before. So now the preventive effectiveness is a 4 because they have engineering control here. So that changes the risk prevention number to 3.75 from 15. That's pretty dramatic. Now, the other way of doing this would be in your severity. Now, just do that back in the severity so you don't get a 15 here in column 14, but that's fine. The preventive effectiveness is not a bad idea. You can see the high preventive effectiveness number will greatly reduce the risk priority number. What do you know about a failure mode and effect analysis? FMEA, it starts out looking like a what-if checklist, and then adds another one after it, what-if checklist kind of, after controls are done. It's not a bad idea. It's a good thing to go through. There are also scenarios where detection of failure number is used, much like the prevention effectiveness number, since a failure that is easily detected will most likely result in less severe consequences. These are things that should be decided when establishing the context. And you think about it for a little bit, that makes a little bit of sense. You have to look at each case on its own merits, but if something that might happen is pretty easily detected, chances are you can get to it or stop it before there's a lot of damage. So risk management process generally consists of these steps. Again, establish the context, risk assessment, risk identification, and then risk analysis. And that's where we're at now. We'll cover the next two as we go. That's it for this one. And thank you, and see you later.